Okay, welcome back everybody to what I believe is part 4. Yeah, I believe it's part 4, yeah. Of Solubility Product Constants, KSPs. And for this part of the series, I'll be talking about common ion effects. And again, the compound we're focusing on is magnesium fluoride. So again, we're dealing with common ion effects. So let's just look at a quick example. Let's put magnesium fluoride on the side right here so that we know that we're dealing with this. And let's write the expression for this. Mg2 plus, and we have F minus squared, and this is equal to the KSP, which is 5.2 times 10 to the negative 11, I believe. Yeah. Okay. So, first thing is first, okay? I want to talk a little bit about this expression, okay? No matter what, okay, no matter what the deal is, that the KSP is always going to be 5.2 times 10 to the negative 11. And this expression is going to adjust itself accordingly in order to get this 5.2 times 10 to the negative 11 value, okay? So, for example, if we have a certain value of magnesium, say we have a little bit of magnesium, then we're going to need a lot of fluorine to make sure that we have this 5.2 times 10 to the negative 11. And the same thing applies if we do it backwards. If you have a little bit of fluorine, we need a lot more magnesium in order to get this value, okay? So this value is always true. This value never changes. This system right here, these values will adjust itself accordingly in order to get this value at all times, at whatever cost, okay? So, with that in mind, okay, let's just say we have in a beaker, right? We have a few, man, that's a garbage looking beaker. But anyways, we have this beaker here, right? And we have it filled up with a little bit of water. And inside there's a few fluorine ions, okay? We'll just say there's a concentration of 0.10 molar fluorine ions in there, okay? So, and on the side we have this, and imagine you're inside in your lab for your general chemistry class, and most likely you won't do this type of experiment, but let's just say that you do this type of experiment and you have this big chunk of magnesium fluoride and you dump it in here into the beaker, and your professor is just asking to see how does the solubility of magnesium fluoride, how does it change when you have a common ion. Well, if you guys read inside your textbooks or lectures from your professors or teachers, if you guys are taking AP chemistry, you guys will know that by reading that if you have a common ion, it decreases the solubility. A lot of times people don't know the reasoning behind it, okay? So again, it's 0.10 molar. Okay, and I'm gonna try to do my best to try to explain why does the solubility of magnesium fluoride decrease if you toss a chunk of that into here when you already have something present. Well, if you think about it, 5.2 times 10 to the negative 11 is a pretty small number, right? It's like 0.00000. It's a lot of zeros, okay? A lot of zeros. So, again, referring back to the statement I made earlier, that this expression is always true, no matter what. So, if we already have 0.10 present, okay? So let's just say, for example, Mg2 plus, and we have 0.10, right? And it's squared. For example, is going to adjust itself to get this value here, 5.2 times 10 to the negative 11. Well, that means that this magnesium concentration will have to be pretty small. Okay, again, remember what I was talking about? If this is big, then this will need to be small in order to get this. If this is small, excuse me, if this is big, then this one needs to be small in order to get this value. Okay, it's just like a balance. You know, if you have if you put something on this side, put something heavy on this side, let's put H over here, then in order to balance out that side, you may have to put something even more heavy. It's just that concept, okay? It's balancing the system. And again, so we have something really big here, so we will need something very small here, right? And this small value, again, this magnesium concentration that's going to be small, again from our predictions, so that this statement is always true, will have to come from here. So if the magnesium concentration is going to be really small, that means the degree of which this magnesium fluoride chunky solid dissolves will have to be small, because again, the magnesium comes from this chunky solid. So in order for this to be small, we need to dissolve just a little bit of this, right? So therefore, the solubility of magnesium fluoride will be very little. It will have decreased. Okay, so now we'll go through the calculations and see if our prediction and our intuition about this whole concept of common ion effects is correct. So let's just do this quickly. Okay. So again, the compound, I'll just draw the little diagram right here on the side. Again, it's really good to have an understanding of what's going on in the solution and what's going on with these problems, not just plugging in some numbers and figuring out the answer. Even though at times I like to do that myself. So magnesium, let's draw that chunky magnesium fluoride, MgF2. Okay, right there on the side. And again, we're dumped that inside here. So let's make our prediction right here. Solubility decreases. Or we could say molar solubility decreases, right? Because it's almost the same. It's basically the same thing. Molar solubility or solubility decreases, or let's put an arrow down. Okay. So magnesium fluoride, solid, Mg2 plus, right? Our typical reaction, right? So our common ion was fluorine, right? It's a common ion because it's common to this beaker and it's common to this reaction, right? So fluorine in the beaker is also found in magnesium fluoride, right? And that's why it's called a common ion. So we'll do our little ICE table, ICE, right? So like I said earlier, we have 0.10 molar F minus present in the solution right here already, okay? So we have 0.10 molar of that present in the solution. So initially, okay, we have no magnesium, okay? Just imagine we just dumped this magnesium fluoride into this beaker. You know, the reaction is just beginning to start, so initially we don't have anything. But we do have fluorine present already, so it's 0.10. Okay, and at the end of this calculation, we'll compare our values, our equilibrium values, and our solubility, molar solubility, to the molar solubility if we did not have a common ion. So we'll see if our predictions are correct. So again, some magnesium fluoride is going to dissolve, and our guess is going to dissolve slightly, very little, because we have this common ion. So plus X, right? Plus 2X. And then again, the equilibrium value will be the initial plus the change. So it will be X, and it will be 2X plus 0.10. Okay? So again, let me write our little expression here. It will be Mg2 plus, right? It will be F minus squared, and that equals our KSP, right? Now let's plug those values into these corresponding slots. So for magnesium, we'll put an X, so X and 2X plus 0.10 squared, right? and it's equal to our KSP value. So let's see what that is. 5.2 times 10 to the negative 11. Okay. So now in this case, we're stuck with a quadratic. You know, we didn't really deal with this in the previous examples, but in this case now we're dealing with a quadratic. So how would we go about dealing with this? Well, your professor or in your textbook you might have seen something where you can sometimes ignore a certain value, and in this case it will be this value. Okay. Well, why can we ignore it? It's because the X value, again, is basically the molar solubility, right? It will be the value of which the magnesium fluoride dissolves. Okay, that should make sense. Now, if that's the value that it dissolves, we know, and our guess is that it's going to dissolve to a very small extent, right? It's going to be really, really small. So if it's really small, right, if this X value is going to be really, 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 really small, and we plug that into here, multiply by 2, it's still going to be really, really small. And in essence, it's not going to really affect this 0.10. So we can just ignore it. And at the end of this calculation, we can check to see if our assumption, our guess to just ignore this value right here was correct, because we can then plug in that X value and see if it really did affect or did not affect it. Okay, so for now we'll ignore this 2x. Okay, so now we have x times 0.10 squared. Let's get our calculator. You guys should know how to do this in my head, but it will be 0.01, and then we divide this out through here, right? And then we get our X value. Okay, first square this and then divide it out here and here, and it will be 5.2 times 10 to the negative 11 divided by answer. Okay, well, I got an X value of 5.2 times 10 to the negative 9. Okay, and so this value right here, we plug this back into this X right here, we plug it into this X right here, and we get our equilibrium values. Okay, excuse me. So again, the magnesium concentration we figured out at the end will be, so the Mg2 plus concentration is 5.2 times 10 to the negative 9 molar, right? And the, what is this, the fluorine concentration, so if we multiply 2 with this value, it'll be really small. Okay, so I'll just do it just to prove to you guys it'll be small. It's 1.04 times 10 to the negative 8, and that's like 0.0000000 whatever 104. Okay, so that's really small, and if you add that with 0.10, it's not going to make a difference. Okay, so our concentration of fluorine at equilibrium will be 0.10. So fluorine concentration, okay, let's put a division here so we can know what is which is which, is 0.10 molar. Okay, so there you go, fluorine is 0.10, magnesium is 5.2 times 10 to the negative 9. So let's address the question now, okay, about the solubility. Our guess, the whole point of doing this calculation was to see if the solubility of this decreased. Okay, so initially, when we didn't have any common ion, right, when we didn't have this 0.10 here, we calculated in the previous parts of these videos that the molar solubility was 2.4 times 10 to the negative 4 moles of magnesium fluoride per liter, right? Well, now it's 5.2 times 10 to the negative 9 moles per liter that dissolve, right? Again, how can you tell the molar solubility? Well, in order for us to generate 5.2 times 10 to the negative 9 magnesium ions, we needed 5.2 times 10 to the negative 9 magnesium fluoride compounds to dissolve. Okay, That's how we were able to generate this value of magnesium ions. Okay, and again, I explained this earlier through this example, so you guys should have a solid understanding of molar solubility by now. Okay, again, in order to generate 5.2 times 10 to the negative 9 moles per liter of magnesium, we needed the same amount of this compound to dissolve. Okay, so the molar solubility when we have a common ion is 5.2 times 10 to the negative 9. When we didn't have a common ion, it was, so let me erase all this because we already have our values. So erase all these calculations and compare. Okay, so common ion. Okay, if I can spell properly, common ion. It was 5.2 times 10 to the negative 9, and this is again the solubility. Okay. Now, if we know common ion, it will be 2.4, right? We calculated this earlier. 2.4 times 10 to the negative 4, I believe, moles per liter. Moles of magnesium dissolved, yeah, magnesium fluoride, yep. So, moles per liter, again, molarity is moles per liter, okay? So there you go. No common ion, it was 2.4 times 10 to the negative 4. A lot of it dissolved in water. We have a common ion, 5.2 times 10 to the negative 9. So again, that's 0.00. For those of you who don't like scientific notation, write it out for you guys. 0, 0, 0. You guys are killing me. Let's see. 0, 0, 1, 1, 2, 3, 4, 5, 6, 8, 5, 2. Okay, moles of that, and it'll be 0.00024. So that's a larger number, obviously, than this, right? This is extremely small. So that much of magnesium fluoride dissolved when we had no common ion. Okay, so there you go, and that is our problems dealing with common ions. So I hope you guys enjoyed this. Okay, and you guys should get some more practice with this if you guys are a little bit shaky with this concept, but I think you guys should be good. Okay, so stay tuned to part, I believe, 5, where I discuss different sources of ions. Okay.